Um, I'm Nilufar. I'm PhD candidate at Clemson University. My research centers on different applications of computer vision and multimodal learning, and more recently, my recent research interest is generalizable adaptation of vision language models. Today, I would like to start with an introduction on vision language models, their different architectures. Then I would like to talk about CLIP, one of the popular VLMs, in more details. I would like to talk about two of my recent works in this area, and then we will continue with data sets and benchmarks that state-of-the-art works utilized to compare the methods. And finally, we will talk about open problems and future work. What are vision language models? Let's start with a definition. Vision language models are AI systems that they jointly understand and connect visual information and natural language. Their goal is to learn a shared representation where both modalities, vision and language, can influence each other, to enable different tasks that can be reasoning, categorization, understanding, and generation. Actually, these large vision language models are usually pre-trained on a really large scale training data. That this large scale training data make them able to be utilized on different applications with a really light fine-tuning process, or even without any fine-tuning or adaptation. And we will talk about it in more details in the next few slides. Let's have a look on different applications of VLMs. As you can see, one of the applications that is really popular is VQA. For example, we have a photo, we ask a question about it, and VLM easily answer to our question. Other application is image captioning, that we can ask for for example, single sentence question, or even we can ask for a detailed caption. As you can see here in the caption, there are a lot of detailed information of the actually image. As you can see, it says a fluffy cat is lying on a sofa surface, sleeping peacefully, a lot of detailed information. Also, image text retrieval, that we have a text query and the network should find the correct match. But in addition to these applications, there is an outside knowledge visual question answering that, this is more challenging than the other applications. Because in these scenarios, the response doesn't directly exist in the photo. For example, as you can see, here is a good example. What sort of vehicle uses this item? The answer is fire truck, but you can see that there is no fire truck in the photo. In such applications, in such questions, actually the network should do some search on the internet, or, for example, use its prior own knowledge. So such applications, such questions are more challenging for the VLMs. So we can categorize VLMs based on different aspects, based on their architecture, how visual and textual components are structured, or based on their training objective, the supervision or loss guiding alignment. For example, they are utilizing contrastive loss like KLIP, or generative loss that enable them to do tasks like captioning, reasoning, like lava, or instruction tuning. Also, we can categorize them based on the modality interaction. When and how image and text features are fused. We have late fusion of modalities, early fusion of modalities. Let's take a look on some um, state-of-the-art VLMs. As we can see here, we have contrastive language image pre-training model, CLIP, that it is one of the earliest and popular VLMs. Here we have two separated text encoders, text encoder and image encoder, that they are trained using contrastive loss. We will talk about the training process and challenges of CLIP in more details in the next few slides. But before that, let's continue with some other popular VLMs. Here you can see BLIP. BLIP is an encoder-decoder VLM. As you can see, we have image text contrastive loss here that is similar to what we have in CLIP, image text matching and language modeling loss. That actually we have encoders and decoder. This enabled the BLIP to be utilized for reasoning tasks and actually captioning tasks, while, for example, contrastive only based approaches, VLMs like CLIP, they cannot be utilized for reasoning or captioning tasks. But here in BLIP, all the encoders and decoder, they are all learnable during the training. So as it is predictable, the computational cost is very high. But there are other kind of VLMs that, for example, Lava or Bilip version 2, that in such VLMs, we have a frozen image encoder and also, for example, LLM decoder, that the LLM is the brain in such VLMs. All the parameters are frozen and they just utilize a mapping to make prepare and ready the embeddings of the vision, because LLM is trained on only language modality, and to fit the embedding of the vision, embedding of the image, we need to, for example, map the dimension of them to be appropriate, to be fit to the LLM. And so in such models, the computational cost is by far less than, for example, models like Blip version 1. Uh, Today, actually, I would like to talk about Kilib in more details. It is trained on more than 400 million pairs of text and image. This data set is really huge. It is collected from the internet. As we can see here, they train these encoders, text encoder and image encoder, using contrastive loss. They apply the cross-entropy loss both horizontally and vertically, because each time they consider, for example, each image as a query, and the other time they consider each text as a query, and compute its cosine similarity, the cosine similarity between the text embedding and each of these embeddings that come from the image. But during the inference, it's really simple. Consider we have in the test set, we have 5 different classes: plane, car, dog, something else, and bird. They consider only a simple template, a photo of the name of the class, and feed it to the text encoder. And it is our actually image query. The only thing that we need to do is to compute the cosine similarity between the embedding of the query and each of the classes. Let's say that here the value of cosine similarity is more than the other ones, so we can say that this query image belongs to this class. But there's a problem. It's not that simple. Here you can see the examples. Caltech is one of the popular benchmarks for image recognition. You can see that in this dataset, adding the 2 words photo of before the name of the class reduced the performance by 2%. Also, adding the word A before the name of the class improves the performance by more than 5%. So, CLIP is really sensitive to the input to the text encoder. We need to do prompt engineering. But the problem is that it takes a lot of time. And even after taking that time, we are not 100% sure that our template is the best. So in co-op in IJCV 2022, the idea of prompt learning instead of prompt engineering was introduced. They proposed that instead of fixed words, fixed templates, let's consider learnable vectors in the input of the textual encoder. But again, that was not that simple. You can see that in the test time, in the case of base classes means the classes that for the few shot learning, we have some samples from them. The model sees some sample from these classes. During the inference, for the base classes, yes, the performance of prompt learning is better than the zero-shot clip. But when it comes to the novel classes, the performance of the prompt learning approach is even worse than the zero-shot clip. And it shows us that there is an overfitting problem here. Actually, to address this overfitting problem, here I would like to talk about Style Pro, one of my recent works. In this work, we are trying to address the problems that we talk about. The domain shift problem, the overfitting problem. In this work, we propose two main approaches to actually address this problem. One of them is utilizing regularization, consistency regularization, and the other one is a style shift learning. Let's start with consistency regularization. What does it mean here? It means that here we are trying to align the embeddings of the prompted encoders with the frozen ones, because we do not want to deviate too much, during the prompt learning, because the original clip itself has a lot of, has generalizable information. It was trained on a really large scale training data. So when we are trying to adapt it with few shot learning, we need to be careful that do not actually forget those information. So in this work, we use both feature-based and score-based alignment. The other thing is a style shift learning. It means that actually, we know engineers, researchers, when they want to make their network robust, they utilize augmentation approaches like random cropping, flipping, or adding, for example, Gaussian noise to the samples. However, these are not good enough for real-world scenarios. So in this work, we are proposing another approach. Here we are using a highly cited paper. That this paper was in 2017. It shows that whenever you wanna keep content information of the image and just change the style, for example, this is your desired image, keeping the content of it, but change the style. The only thing that you need to do is using a pre-trained encoder, fit the image to it, and then channel-wise normalize the feature maps, and then use the mean and standard deviation of your target style. By this way, you are removing the style from your content image, preserving the content, but changing only the style of the photo. If you actually fit this synthesized feature map to a decoder, now the reconstructed photo will have your desired characteristic. But in this work, because of the computational cost, we don't reconstruct images and then fit to the encoders. We just use the synthesized feature maps here and then fit the synthesized feature maps and the original ones to the rest layers of the network. Also, Also, in this work, we do not have a mean and a standard deviation. I mean, we don't have any information about the style of our target. The only thing that we have is a few samples to just do the adaptation. So we try to learn these style bases. We try to learn mean and standard deviation. So here we utilize two losses to learn these style bases. One of them is diversity loss. The other one is content loss. Diversity loss here means that we want to cover the whole hypersphere. It means that we want to learn styles that they are not similar to each other. We want to cover more styles. So we try to minimize the cosine similarity between different learnable style bases. The other one is content loss. It means that we want to make sure that the content in the feature maps, generated feature maps, has been preserved, and the only thing that has changed is a style. So we compute the cross-covariance matrix between the synthesized and the original feature maps, and the diagonal items on it need to be close to 1. I talked about the self-consistency regularization, and let's also take a look at DISA, the other work that we proposed to address the overfitting problem. Still in this work, we are using the self-consistency regularization because it is really helpful. It is a really powerful approach. But here there are two main differences between this work and the previous one. One of them is, in this work, we utilize actually class-wise feature means for that alignment. Instead of image-to-image alignment, we align with the actually reliable prototypes that they are class-wise feature means, because each of them has more characteristic, information from each class instead of single sample from each class. The other thing is saliency mapping, because after a few iterations during the few-shot learning, the actually prompted encoder over rely on some patches that they may not be that informative, but the original clip, the original encoders, they have more generalizable information. They are more able to find and detect actually patches with more important data. So we utilize the guidance from the frozen encoders to help the prompted encoder to still focus on informative patches. Let's take a look at the benchmarks for comparing methods with each other. One of them is based to novel generalization setting. All the state-of-the-art works usually utilize this setting. This is a simple setting, we utilize 11 data sets. We train our model using few samples each class. But during the test time, we have samples from seen and also unseen classes. And as it is actually predictable, the performance of all the methods on the unseen classes is less than the base classes. But the other challenging setting is cross-dataset evaluation. In the previous setting, actually the dataset for the test and train was the same, just we had some new classes. But here, we train on a completely different dataset like ImageNet, but test on, for example, other datasets like Caltech, Oxford, and as you can see, in comparison to the previous setting, the performance of all methods here are less than the previous one because it is more challenging. However, you can see because of the alignment approach and also a style shift learning module, saliency masking that we utilize, is still our both methods are outperforming the other ones. The most challenging scenario is domain generalization, because here you can see some samples from ImageNet that we use for training. But when it comes to testing scenario, we test it on completely different domains like ImageNet rendition, ImageNet sketch, ImageNet adversarial. So it is the most challenging scenario for the VLMs. And as you can see, the performance of all approaches are, somehow around 60%. But still, StylePro and DISA are performing better than the other ones. What about open problems and future directions? There are some challenges that we talked about them. They are somehow more related to the clip style VLMs, like prompt sensitivity that we talked about, or overfitting in adaptation. But the other problem that we didn't talk is lack of local grounding. It means that, Clip aligns whole images with text, but lacks region level grounding because the whole image is matched with the whole description during the contrastive learning. So it cannot learn the details of the caption or details of the photo. Also, weak attribute binding. Clip often ignores word order and fails to correctly link attributes with objects. For example, it is confusing for Clip to understand a difference from yellow bus with a blue bus. But these actually challenges are more specific for clip style VLMs. What about more general VLMs, like, for example, Lava, Gemini, Cohen? Maybe you have heard about hallucination. For example, in visual hallucination, model mentions objects or attributes not in the image or cited the wrong region. Let's see an example here. The question is the person drying her hair? And actually the VLM here makes mistake. It says, yes, the person is drying her hair with a hair dryer, but it's not correct. It happens because, during the training, most of the samples, whenever they include a hair dryer, there is someone that is drying her or his hair. So, it is biased on its training samples. The other problem is over reliance on language cues. Because, most of the VLMs, including Lava, in the last layers, the effect of a language modality will be more than the tokens that come from the vision. Because the LLM itself, it's trained on language modality. So there are a lot of works that they are recently trying to address this problem. So there is a lot of room here still to be worked on it. Another thing is uncertainty and calibration. I think that many of us have worked with ChatGPT. For example, when you ask a question, in most cases it tries to give us some answer, while maybe it doesn't have any information about it, or it is not trained on such actually data like medical applications, or for example remote sensing applications, but it uses some search, find some similarities, and give us a response that it cannot be correct. So still there's a lot of room here to work on it. The other thing is safety, privacy, and copyright. Sometimes we use LLMs to rewrite our CVs, to edit, for example, our cover letters or something like that, that they include our private information. As VLMs usually utilize continual learning, they utilize such inputs to improve themselves, and it can be, unintentionally misused for some other applications, for to answer to questions to someone else, that it's really important to work on it. The other thing is Fixed visual resolution, VLMs are usually trained on fixed size inputs. When we feed images with high dimensions, they use scaling, and so they cannot concentrate on questions that need detailed information. For example, here you can see an example. It cannot detect the number, here correctly. It says that the player who is shooting is wearing the number 10, while it is 8. It cannot detect detailed information and pay attention to the correct and important pixels because of the scaling. And also about buoyant RGB, because we talked about it, different applications like medical, it struggles with depth, thermal, and medical images due to the distribution gaps and limited label data. So whenever we are trying to adapt them for these applications, we need to find efficient ways to give the network some hint or adapt it for such scenarios, because we cannot use zero-shot scenarios for these applications. VLMs are usually trained on common photos, RGB images. And the final thing, last but not least, is in context learning. Sometimes we do not need any training stuff. We can simply use demonstrations. For example, for VQA tasks, we can fit some, photos, a photo, a question, and the correct answer. We can utilize 10, 20 of such triples and give the network a hint that, look, whenever we are asking you such questions, we are expecting to actually get such responses. But there is a computational cost here. Also, the performance of the VLM is very sensitive to the order of these demonstrations, which comes first. Or, for example, which demonstrations we are going to choose from our data set. All of them are still challenges that people are currently working on them. And here you can see some of the key references, and if you have any questions, I would be happy to answer.